afternoon, everyone, and welcome to the Parsons Technical Webinar Series. I'm your host, Jessica Bennett, and today we have with us Dan Griffiths, who will be presenting on innovative applications of hot ISCO for in-situ and ex-situ destruction of PFAS. A few housekeeping items first. We'll be keeping all phone lines muted during the presentation to keep any background noise down. If you have questions during the webinar, you can either hold on to them to ask at the end during the Q&A session, or you can enter them at any time into the chat feature, and we'll answer them at the end. This webinar has been approved for Unprofessional Development Hour credit, or PDH. If you'd like to receive a PDH certificate, there'll be a link posted in the chat a couple times throughout the webinar. There are several multiple choice questions you'll need to answer, so please take a look at those in the chat in case you can't access the form during the webinar. And if you have any issues with getting that form, just let us know and we can follow with you after the webinar. And finally, this webinar is being recorded and will be posted on our YouTube channel in the next few days. So a brief agenda for today's webinar. We'll first introduce our guest speaker, Dan Griffiths, followed by a core value moment. And then we'll get into the technical presentation and wrap up at the end with Q&A. Next slide, please. So a little bit about Dan Griffiths. He is the Parsons Innovation and Technology Director, as well as a Subject Matter Director for the Groundwater Restoration practice here at Parsons. He has over 20 years of experience specializing in emerging contaminants and complex environmental investigations and remediation. And he's also a registered geologist and a Parsons Fellow. And with that, I will hand it off to Dan for the core value moment.
Thanks, Jess, and thanks everybody for joining and giving us an hour out of your busy day. I'd like to start these presentations with a core value moment. As you're all aware, likely at this point, Parsons has 6 core values: safety, quality, integrity, diversity, innovation, and sustainability. And given my role and given the content of this presentation, I thought I would focus on innovation for today. So Parsons is a highly innovative company, both in our environmental fields as well as our other business lines. We're recognized in the industry for our innovative approaches to site investigations as well as remedial action plans. We also have a pretty extensive internal research and development program across the company and in the environmental practice. We're focused on developing technologies and solutions for the industry to help our clients develop better options for their sites and to move the technology practice forward. We run an environmental R&D lab in Syracuse, New York, where we do all of our internal research and development work. And we also partner a lot with our industrial partners and our academic partners to develop new technologies and new means to do things better. Some of our recent projects, which really focused on innovation, are projects that are focused on emerging contaminants, like a site we have in South Carolina. We developed a phyto and enhanced bio remedy for 1,4-dioxane site that allowed us to address 1,4-D on that site, stop a plume from migrating off the site at low cost and at very effective means. We also have a number of other sites that you can see in the list there in the middle. That's just a few examples of the sites that we've tackled using innovative approaches and new technologies that we either developed in-house or that were developed in the industry. As part of our R&D practice, we also try to protect our IP. We have a number of patents that you see on the right-hand side for technologies that we've developed. One of those is hot ISCO. And just a few more words on the R&D program. We really developed the R&D program to allow our technical experts the opportunity to dive more deeply into the contaminants that we work with every day, to better understand how the contaminants work, and more specifically, how to address those contaminants, hopefully through destructive means in the environment. And occasionally through that R&D program, we produce something really cool. And an example of that is hot ISCO, which I'll be talking about today. Now, I think at this point, we all know what PFAS is, where it comes from, how it moves in the environment. So I'll just spend a few minutes talking about some aspects of PFAS that are important with regard to destruction technologies, and how to apply those destruction technologies in the field to address PFAS. As we're all aware, there are something like 14,000 or 17,000, depending upon the paper you read, PFAS molecules in existence. And they're all consistent in that they consist of a carbon backbone, which has a bunch of fluoride stuck on it, hence the fluorinated compound. They're all organic in that they have that carbon backbone, and they all, they range from very short C2 carbon, 2 carbon chain length, all the way up to, 20 or more. So huge variety of structures. There's also branch structures, linear structures. So there's a wide variety of structural types within the PFAS universe, which makes them more difficult to degrade and honestly more difficult to understand in terms of how they move in the environment. In addition to the simple structure you see on this slide, we also have the Gen X compounds, which are C6 compounds or 6 carbon chain length compounds that are a whole different aspect of the PFAS universe. Simply put, most PFAS compounds out there are, they consist of a carbon backbone, which I've said, but they also have a functional group at the end. On this slide, it's pictured on the left side as the yellow and red dots. They're consist of oxygen, sulfur. They're negatively charged or positively charged depending upon the PFAS molecule. And typically, when you talk in the industry about PFAS destructive technologies, most of the technologies out there currently are really transforming technologies. They're not destructive technologies in that they transform the PFAS molecule into something else, either through deletion of the active head group or deletion or shortening of the carbon chain, but they still produce PFAS molecules in that they're changed, they're modified, they're either non-functional or they're shorter chain. Here at Parsons, when we talk about PFAS destruction, we mean destruction down to the end components, the fluoride and carbon dioxide. So we don't mean transformation. We are focused on developing technologies that really destroy the PFAS molecules all the way to the end products, carbon dioxide and fluoride. Hot ISCO is no different. The focus from really start of our research path was to develop a technology that would be able to completely destroy PFAS in the environment. And moving along, PFAS, much like a number of other contaminant classes, it's a complex mixture. PCBs are also a complex mixture. Hydrocarbons are a complex mixture. But the difference with PFAS is that not only is it a complex mixture, it's also very stable in the environment, and it's very mobile in groundwater. And this trifecta of risk paradigms means that PFAS is more difficult to understand in the environment and more difficult to address and degrade. This really results in a pretty limited number of PFAS technologies that are available on the market to address PFAS in the environment. Right now, you have the physical removal and physical containment in terms of pump and treat or excavation. You have incineration for destruction of PFAS in an Ex-Situ setting. But all of those technologies are very energy intensive. They require pre-treatment, particularly in the Ex-Situ environment, and they're also very expensive. And as we move forward into the PFAS universe, I like to, at this point, liken it to the chlorinated solvent universe. We really are, if you look at the chlorinated solvent timeline, in the early 2000s. About 2001, 2002, the industry believed that chlorinated solvents were very recalcitrant, very mobile, and very dangerous because they couldn't be degraded. But, as the industry progressed, new technologies were developed. And at this point, chlorinated solvents are the easy contaminants. PFAS is on a very similar trend, although I think much accelerated. So in the next few years, you'll see drastic improvements in terms of remedial technologies that are available for use, in terms of effectiveness as well as declining cost. Hot ISCO is a great example of that. It's one of the first technologies that will be fielded that is capable of destroying PFAS in Ex-Situ and In-Situ applications, but there will be others. So just a few words on our R&D program. Again, Hot ISCO is a technology that came out of our R&D program. Our R&D program is entirely funded by Parsons dollars. We see it as a good investment in terms of developing better solutions for our clients and for the industry. And we'll continue to work on PFAS as well as other emerging contaminants. Currently, we're working on about 11 PFAS related internal research and development projects, one of which, of course, is ISCO, but there's a number of others that we're working on to just develop better solutions for the industry. Now I'll jump into ISCO, and I'll start with just telling you what ISCO is and how it works, and then we'll dive into the results, which I think is what most people are most interested in. So ISCO is a technology, again, that can be applied in situ or ex situ. It's a destructive technology in that it's capable of destroying PFAS all the way down to the end, end constituents, carbon dioxide and fluoride. And it's it combines a low thermal energy rise. So from a typical ambient groundwater temperature of 20 C, we need about 10 to 15 degrees increase in temperature up to the 35, 38 degrees C range. And then we apply a combination of a catalyst and a standard off-the-shelf oxidant, typically persulfate products. The combination of the energy applied through that small temperature rise and the oxidant and the catalyst, which allows us to use that energy more efficiently, results in the destruction of the PFAS molecules or the PFAS mass. The catalyst is mostly silver. In some cases, we apply a bimetal catalyst, depending upon soil mineralogy as well as groundwater geochemistry. But it's mostly silver, and it's applied in a very carefully controlled manner, such that we can get the right balance of catalyst, oxidant, and temperature. And again, the oxidant is just an off-the-shelf persulfate product. When we started the whole development journey, initially we were working at very high temperatures in the 50 to 60 degrees C range. And we've really spent the last 2.5 years, 3 years at this point, driving that temperature down through the application of the catalyst and balancing that with the oxidant, such that we finally are at the point where we can apply this technology at reasonable temperatures that you can achieve through solar heating. Wherein you don't have to put in like an electrical resistive heating application, which makes the technology much more flexible and much lower cost. And in terms of our research work, we started this in 2021 with some proof of concept laboratory studies, and that moved on through 2022 and 2023 to find the best match of catalysts and oxidants and the lowest possible temperature. And you'll see down below that we're continuing to optimize this technology so that we can further reduce the cost of application and the amount of catalyst and oxidant we have to put in the ground, which makes it more attractive and reduces the cost. At this point, we've completed 41 studies to date. All of our studies are completed in triplicate, and all of our analytical work is done by a third-party commercial lab, typically PACE or Eurofins. All of the data that we collect is validated, which gives us high confidence that the performance and the results that we're seeing and that we'll talk about later in this presentation are real. They're fully validated. They're based upon data that is produced through a third-party commercial laboratory, which gives us a lot of confidence. For analytical support, we started with 537. When the industry moved to 1633, we did as well for our internal R&D work, including ISCO. And in the more recent studies, our analytical work, 1633, is supported by total organic precursors, total organofluoride, total inorganic fluoride analyses to demonstrate that we're really getting PFAS destruction, not just PFAS transformation. And through this whole process, we finally developed an iterative process that we understand well at this point that consists of one catalyst application. In an Ex-Situ approach, it's adding catalyst once to your tank of water, your drum of water. In an In-Situ application, it's injection of that catalyst one time, followed by multiple oxidant applications to achieve the desired results. And the key here is that you only have to put the catalyst in once, and then you calibrate your oxidant applications depending upon your remedial goal. As an example, if you're applying this technology in a source area, perhaps your goal is only to reduce your PFAS mass, an order of magnitude, to reduce mass flux into your down gradient plume. You can calibrate the number of oxidant applications you you put in, which allows you to optimize your cost of your application to meet your objective. If your objective is to achieve, 4 or 5 nines destruction, 99.99% destruction, and achieve, say, the US EPA's MCLs, you can do that. You can achieve those very low numbers, but it's going to take a large number of oxygen applications, and of course, it's going to lead to a higher cost. So the technology is really infinitely flexible and infinitely optimizable based upon your remedial goals. Okay, so the chemistry is actually relatively simple. On this slide, you see a couple pictures, 5 pictures at the top. It's the same bottle, and it's going through the hot ISCO application process, and then a little bit of chemistry in the lower right-hand side. Essentially, at 0 seconds, which is the bottle on the left, we've added our catalyst, which is soluble in its +1 state. And then as you move to the right, the second bottle is after we've added our oxidant. Addition of the oxidant converts our metal catalyst from a +1 state to a +2 state. In the +2 state, our catalyst is non-soluble, so you see it started to drop out of solution in the third bottle from the left, the dark colored bottle. You see that precipitation. And then as the oxidant is broken down to produce the radicals react with the PFAS in the bottle and the catalyst, destroy the PFAS, and convert the +2 catalyst back to +1. In the +1 state, it's soluble, goes back into solution, and at the end on the right, you end up with a bottle of clear water, and the PFAS in the bottle has been destroyed. Now, this is, again, a iterative process in that you add the catalyst once, and then you iteratively add additional oxidant to destroy more and more PFAS mass. After the first oxidant injection, you've generally destroyed about 10 to 15% of the PFAS mass in the bottle, and you add additional oxidant applications to destroy more and more PFAS mass, again, making this technology infinitely flexible and infinitely optimizable. So that's the technology and the science behind it. I wanted to spend most of the time in this presentation talking about results, because the results are really most important. And I'll first talk about results related to PFAS derived from firefighting foam. Most of the results that you'll see are from impacted sites. They're real soil and real water samples that we collected at sites that we work on. And then for the second half of the results presentation, I'll talk about results related specifically to PFAS derived from Gen X and from plastics. So early on in the development process, we started with PFAS derived from firefighting foam. That was where the industry was most interested in, where most of our clients were focused. So we started with firefighting foam derived PFAS. Some of our early lab studies are shown graphically on the right and in the text on the left. And early on, we were achieving destruction in the 70% range. 70% of PFAS mass was being destroyed. And we saw a wide variety of destruction potential based upon PFAS molecule. Early in this presentation, I talked about the different PFAS structures, and there's a whole variety of structural elements for PFAS molecules. There's branch, there's linear, etc. Well, we see that in the results. In some cases, some PFAS are really easy to destroy. In other cases, not so much. And that's why the development process for the technology took us 3 years to perfect. Again, the catalyst is only applied once. We developed that early on, and it's recycled every time by the injection of additional oxidant. And in further studies in year 1, which would be 2021, we were achieving 90+% destruction, again dependent upon specific PFAS molecules. And some of the key takeaways for our early work, and these results you're looking at are from a client sample. So these are real samples of soil and groundwater collected at a site. We applied hot ISCO to samples of soil and groundwater in a bottle, so there were mixed matrix studies. And very quickly we were achieving good destruction for the PFCA side of the PFAS universe. 98% destruction for PFOA, 100% within our method detection limits for the related compounds. And you can see the results graphically on the right. Initially, we got a actual increase in PFHXA and PFHPA, which tells you that there were some precursors in the water and soil samples that were oxidized to produce those compounds. And then as we applied more and more oxidant, as indicated in the horizontal bar, we were able to destroy the contaminants that we were producing. The concentration range early was relatively low. We were looking at about 50,000 nanograms per liter total PFAS, and we were able to destroy that relatively low concentration, starting concentration, out to 100%, again within our method detection limits. These results are based upon 537 analyses, so the analytical method was 537. Within the same study, I mentioned earlier, some contaminants are more difficult to degrade than others. This is the PFSA side of the PFAS universe. And you can see the destruction that we were able to achieve was significantly lower. PFOS was about 87%, and the related compounds were 30 to 50% destruction. This tells you that the PFSA side is more difficult to destroy using an oxidative approach. And honestly, it's more difficult to destroy for most of the destructive technologies out there for PFAS. PFOS concentrations were significantly higher, about 6.5 parts per million, so very high. And we were able to destroy a good portion of that mass through 10 oxidant applications, as indicated on the horizontal bar in the chart. And you can see, again, a peak in PFOS. So we were definitely converting precursors to PFOS initially in the first 2 oxidant applications. And then through the following 8 oxidant applications, we were able to destroy most of that PFOS mass. Moving on to a larger volume study that we did. This study was done in 2022. This is a drum study, and we were using contaminated surface water from a site, so it's a real world sample. And you can see in the lower right that we were not doing any pre-treatment. That's muddy, dirty water that we collected directly from a surface water body. It's got leaves and sticks floating in it. And our goal was to perfect this technology without any pre-treatment. We don't want to pre-treat because it increases the cost and it increases the complexity. So we simply took the sample of muddy water, put it in a drum, then applied hot ISCO to it with 1 catalyst application, and we went out to 8 oxidant applications in this case. For the PFOA side, we were able to achieve 70 to 99.999% destruction. The PFBA was the difficult compound, and it stuck around. In this case, we were using 537 again, and we were getting 30-day turnaround from the laboratory. So we had to kind of pre-plan, and by the time we got the 8th application results, we'd already taken apart the study, so we couldn't go further. You'll see results down below where we were able to go out to additional oxidant applications, and you can see the destruction percentage continue to increase. PFOS, much like the study before, was a little bit more difficult to degrade. We got about 91% destruction after 8 oxidant applications in this case. But more importantly, we observed that the hot ISCO technology works just fine without pretreatment. If there's a lot of organic in the water, it will increase your oxidant utilization, so it'll increase your cost incrementally. But the technology itself still works quite well. We didn't see any masking or passivation of the catalyst. We were able to recycle it out to, in this case, 8 times. And just moving on, I told you earlier that the later studies were supported by TOP and TOF analyses to ensure that we're actually getting complete destruction, not just transformation. The next 2 slides are TOP assay results for the study we just looked at with the drums. And the takeaways from the top assay are, as you can see in the graphic, the first bar on the left is a sample of the raw water, unoxidized, and analysis of that water, again, using 537 to quantify the PFOA side of the PFAS universe. Relatively high concentrations. And then we took that raw sample and we oxidized it using the top assay. And as you can see, concentrations of most of the contaminants, particularly PFHXA, increased substantially by more than an order of magnitude, which tells you that there's a lot of precursor mass in these samples, and that precursor mass was converted to contaminants that we were measuring within our 537 analytical suite. This is a recurring theme. You'll see it recur in all of the results as we go along. And then application of one catalyst and 10 oxidant injections resulted in 90 to 100% destruction, depending upon the molecule. PFOA, PFHPA, and XA out to 100%, again, within method detection limits. And PEA and PFBA were a little bit lower, 90 to 99%. Back to the graphic on the right-hand side, you see the two bars. Those are top assay analyses of the water after we applied 10 oxidant applications and one catalyst application. And you can see the concentrations are much, much lower, still a little bit of PFBA and PFEA, as you would expect based upon the percentage of destruction. Top assay results for the PFSA side of the PFAS universe. Very similar in that on the left-hand bar, you see results from the raw sample, unoxidized, very high concentrations. And then you move over to the right, that's another sample of the raw water before we applied ISCO to it, oxidized through the top assay analysis, and concentrations of most of our contaminants increased substantially, particularly PFHXS. Again, telling you that there's a lot of precursor mass here, and through the top analysis, we oxidize that precursor to produce molecules that we're actually quantifying with our 537 analysis. And as you would expect, the PFOS side is just more difficult to degrade. We got anywhere from 21% to over 90% destruction. Interestingly, PFBS, we actually produced more PFBS than we destroyed. And you can see that in the numbers on the lower, the bottom of the chart. And, as we went along, after 10 applications, we continued to see additional destruction. So the numbers you see are after 10 oxidant applications. And I'll jump into the Gen X results. These were interesting. We started with the firefighting foam derived PFAS. We thought we learned a lot of lessons and we got really good at destroying our PFAS mass. And then we started into the Gen X, and of course, it really threw us for a loop. We got initial very good result of destruction. We saw our primary contaminants, HFPODA in particular, which is Gen X, were being destroyed, but we were getting even more production and then destruction of our intermediate products, which indicates that specifically for Gen X, there's a lot of precursor mass that's present along with the contaminants or the PFAS molecules that you're actually quantifying, that through an oxidative approach, you oxidize to intermediate products, in this case, your contaminants of interest, and then through additional oxidant applications, you continue to destroy that mass. This is our first Gen X study. We had some challenges. In some cases, some of the molecules were very easily degraded. On the chart, you see concentrations declining pretty steeply for most of our PFAS molecules. We got 100% or nearly 100% destruction for a number of them, but there are some molecules that were problematic. We produced a lot, and then we had difficulty in destroying those molecules. So we essentially went back to the drawing board after we saw these results, and we tweaked our catalyst mix and our oxidant balance and our temperature regime to optimize our ISCO technology specifically for Gen X. So the technology still works, and you'll see that in the following slides, but it needs to be applied differently. The balance of catalyst and oxidants is different. The temperature requirements are a little bit different in that we go a little bit higher into the 40 to 42 degree C range. And with those tweaks, we're able to see really good destruction. And I wanted to point out in detail, this is from the same study where we are producing PFAS and we're sequentially degrading the PFAS. On this chart, you see a series of Gen X derived PFAS molecules, HFPODA on the left, all the way to some really exotic molecules, RPSDCA on the right. And the green bars are 0 day, so that's the baseline. That's what we started with. And as you move to the blue bar, which is 5 days after start or after the 5th oxidant application, you see a lot of changes. And then the red bars are 30 days, and 30 days actually is after 12 oxidant applications. In the case of HFPODA, we were able to destroy it relatively directly. After 30 days, we got good destruction for HFPODA, ending with a concentration of about 6,000, where we started with 24,000. But some molecules were a little more challenging. PFMOAA in particular, we had a lot of trouble degrading that molecule. But moving off to the right, most of the other molecules were destroyed completely or nearly completely through the 30-day application. Very similar trends to the previous bench studies, and you'll see this trend and improvement on this trend as we move forward. So more recently, we did another drum study late last fall. We saw complete destruction of 7 compounds with partial destruction of the rest. This was after tweaking our catalyst balance and our oxidant loading. So we got better results, and as we move forward, we improved. In this case, on the chart to the right, it's degree of destruction for each PFAS molecule. And in most cases, the green bar is 5 days, the blue bar is 30 days. In most cases, we got 100% or nearly 100% destruction. There are a few exceptions. In particular, we have a byproduct that we were not analyzing previously, but we added it to the list. We expanded our list, and we're able to see more and more PFAS molecules. And you can see at day 5, there's a huge negative 250 or 260% destruction, which means that we produced that byproduct. It's an intermediate product that was produced through the oxidation of its precursors. But moving to 30 days, we were able to destroy all of the mass that we produced. So again, a sequential process where you're converting your precursor mass through oxidation to the PFAS molecules that you're quantifying with your analytical suite, and then you sequentially destroy that mass moving forward. A couple take homes there. One is that you really can't rely only on 537 or 1633. Those analyses will give you performance on your compounds of highest interest, but it doesn't tell you the whole story. You need to combine your 1633 analysis with either total organic precursors, so that you're quantifying a larger portion of the PFAS universe and confirming destruction of that PFAS mass, or total organofluoride balanced with total inorganic fluoride, so that you're confirming that you're actually getting destruction, not just transformation to something else that you're not measuring. Moving forward, this is our most recent study. This is a tank study. It's essentially a full-scale study in that we were destroying water collected from a high concentration source area. It's a groundwater source area, so we collected high concentration groundwater from that source area, put it in the tank, and we also looked at a very high concentration waste stream from plant waste. This is a plastics plant, and they were generating a waste stream that had very high concentrations of PFAS, but it also had high concentrations of salt and other stuff. And we really wanted to try ISCO on a very complex matrix, and that plant waste stream was a very complex matrix. In this case, we used 225-gallon tanks, so that we're working with high volumes. And again, we applied one catalyst application and initially 13 applications of oxidant. The starting concentrations were very, very high. You'll see those in the graphs on the following slides. So you can see good destruction in a very difficult chemically and very difficult PFAS concentration waste stream. Study was completed this past March, and all of the analyses, all the sampling events that we collected were a combination of 1633 specialty PFAS analyses, total organofluoride, total inorganic fluoride, fluoride itself, as well as geochemistry, so that we could confirm that we're actually getting the destruction that we think we're getting based upon the PFAS analyses, and to determine how the chemistry in the water changes with the application of hot ISCO. And moving into the results, the chart on the left is the chart of PFAS analyses, and you can see that while they're all going in the right direction, we have much lower concentrations at the end than we started with, so we got great destruction. In a lot of cases, you have initial peaks that we again, we're producing the compounds that we're analyzing for through the oxidation of the precursor mass, and then we sequentially and iteratively destroy that mass that we produced. So we got good destruction. And on the right-hand side, you see a balance of total organofluoride, which is representative of the total mass of PFAS in the tank, against total inorganic fluoride, which is the inorganic fluoride that we produce through the complete destruction of the PFAS molecules. So again, we're producing carbon dioxide and fluoride. And as you would expect, they're essentially mirror image, which means that as you destroy organofluoride or PFAS, you produce inorganic fluoride. And that inorganic fluoride is represented in the blue bar, the blue chart. Increasing trend is exactly what you want to see, matched with a declining trend on the green line, which is indicative of total organofluoride. Now, I'll point out that the TOF and TIF analyses they're difficult analyses, and that you get a lot of variability, and you can see that up and down nature of the charts. So the take home here is it's important to look at the overall trend and ensure that you have an upward trend in TIF, inorganic fluoride, matching your downward trend in organofluoride to confirm that you're actually getting complete destruction of your PFAS mass. So conclusions, on the positive, we have been able to demonstrate the efficacy and performance of the hot ISCO technology at this point in the laboratory on lab-based matrices, as well as real-world samples of soil and groundwater from impacted sites. I think we're out to, actually, I think at this point we're out to 10 states, but when I made this presentation, we were out to 9. And we're continuing to invite, clients and other groups to send us samples so that we can give them a try in the lab, demonstrate the technology works, and expand our knowledge base. Every sample is a little bit different. Every site's a little bit different. So as we run more and more studies on real-world samples, we continue to learn more and understand better how the hot ISCO technology works and how it's able to destroy PFAS. Again, all of our results are based upon validated, robust study design with replicates, controls, blanks, and all of our analytical comes from a third-party lab. We use standard 537 and 1633 analysis methods, as well as specialty non-standard methods to ensure that we're actually getting good destruction. And at this point, we've documented and demonstrated good destruction for all of our various PFAS family units. PFCAs were out to 99.9%, again, within method detection limits. PFSAs, 95 to 99.9. There's still a couple of problem molecules that are difficult to destroy, which gives you the 95% number. And then, Gen X derived, again, from plastics plants, we're typically in the 90 to 99% destruction range. All of those numbers are based upon cost balanced designs. So again, the hot ISCO technology is infinitely flexible in that you can design your application, control your cost based upon your remedial goals. Some of the less good, you can't present the positive without talking about the negatives. Hot ISCO is a great technology, but it's not perfect. The oxidant demand from site to site is highly variable. It's variable depending upon how much organic carbon is present naturally in the site soils. It's also dependent upon the PFAS concentrations as well as the profile, what PFAS molecules are present. And in some cases, the site characteristics will drive relatively high cost, particularly if there's a lot of organic present, and certainly if there's LNAPL present, like there is at a number of fire training areas. The cost to apply hot ISCO is going to be higher because the organic carbon represented by natural organic carbon as well as LNAPL represents a inefficiency and will require you to put more oxidant in. In-Situ performance, just like any other In-Situ technology, is going to be limited for low permeability sites where soils are dominated by, silt or clay. And that's because it's difficult to distribute the reactants. In this case, the reactants are catalysts and oxidants. In, enhanced bioapplication, the challenge is to distribute your organic carbon. So much like all other injection-based In-Situ technologies, hot ISCO performance is going to be limited on low permeability sites. And finally, hot ISCO is a great technology for source areas where PFAS mass is very high, it's concentrated, and your goal is to destroy a lot of mass very quickly. You can do that with hot ISCO. But it's not a technology you would apply in dilute plumes. And it's also not a technology you would apply as a PRB, say, at the plume toe. Because the basis of the technology is to use, a small temperature rise with a catalyst to supercharge the oxidant and to produce very reactive radicals that are capable of destroying PFAS. In supercharging your oxidant and producing super reactive radicals, you're also limiting your reaction time to a few minutes. Your radicals are not going to hang out in groundwater for days on end. They're going to be present and gone within a few minutes, which makes the technology great for source areas, but not so great for permeable reactive barriers. And just a few words on what we have coming up. I mentioned earlier that we're continuing to work in the lab to continue to optimize catalyst loading as well as oxidant loading. We're working in the lab to look at means to recover the catalyst, particularly for Ex-Situ applications, but it's also applicable to In-Situ applications. One of the highest cost elements of hot ISCO is the catalyst. So we'd love to develop a means to recover that catalyst and reuse it. We're working on that now, as well as the reactant loading optimization studies. We also have a field demonstration coming up, hopefully in late this month, early next. It's a box study on a site in Michigan where we're going to essentially rent a roll-off, fill it full of impacted site soils and site groundwater, and do a hybrid, Ex-Situ, In-Situ study on that on those matrices. So that'll be really cool. Hoping to be presenting those results next fall. And last, just a plug, we're looking for partners to work with, either people or clients that are willing to send us samples of their impacted site matrices to play with in the lab. We're also looking for opportunities to demonstrate hot ISCO and PFAS destruction in the field. We do have a budget set aside for next year where we can co-pay a study, so the client doesn't have to pay for the whole thing. We're willing to continue to invest in this technology and continue to learn how to apply hot ISCO most effectively in the field. So if you're interested, please reach out to us, send us a sample of your site water and or soil, We'd love to play with it in the lab at no cost to you, and we'll share the results after we're done. And if you're interested in talking about a field application, we'd be really interested in talking to you about that as well. And that's what I have. I think we have a little bit of time left for questions.
Yeah, thank you, Dan. It was a great presentation. If there are any questions, you can either raise your hand to ask it live, or you can enter it into the chat. Looks like we already have a couple in the chat so far. So the first one is, does the mass of aqueous change into gaseous mass as a measurable difference?
So the mass of aqueous PFAS, of course, changes with destruction. And as you destroy the PFAS mass, it's essentially a sequential breakage of the carbon chain. It's not a one step, it's a multi-step. So not only are you defluorinating, you're also breaking the carbon chains, making the carbon chain shorter and shorter, which theoretically would make the some of the PFAS mass more volatile. But in our limited sampling, we really don't see a whole lot of PFAS, say, in the headspace of a laboratory bottle or the headspace of the drum and tank studies. So I think the destruction process is fast enough that you really are not producing a whole lot of volatile PFAS, and PFAS in general isn't particularly volatile. But it's a good question, and it would be worthwhile to do some additional sampling, especially with the approval of the PFAS in air methods. EPA approved those this past spring, so it would be an interesting add on to a study. I think that what we'll see is very little in the vapor phase or in the air gap, but it'd be worth quantifying and documenting that. Thanks for your question.
Next question is, please confirm that the max concentration after transformation of precursors is used to calculate the destruction percentages.
Yes, to the extent we can. Our destruction percentages are balanced by the production of inorganic fluoride, and we mass balanced as best we can. We never have a perfect mass balance. And much like when you're applying reductive dechlorination to chlorinated solvents, you never mass balance to chloride or the end results, ethene, ethane. And I think that's because in the case of PFAS, the fluoride is pretty reactive. We thought we would have tons of hydrofluoric acid as an example, but we really don't. Particularly if we're doing a mixed matrix study where there's soil in the bottom of the bottle or the bottom of the drum. I think the fluoride is pretty reactive and it drops out as salts essentially faster than you can measure it. So while our percent destruction is confirmed and balanced by inorganic fluoride generation, it's never a perfect mass balance.
Okay, the next question is from Tom Lee. How much time is required between injections? It looks like multiple injections per day.
Yeah, that's a great question. Ignoring the hydraulic mounding that you always get through injection of any fluid, not just hot ISCO, we can actually pile the oxidant applications pretty closely together. The oxidants are again reactive or active for minutes. So conceptually, we could apply additional oxidant applications every half an hour or every 20 minutes if you wanted to. The problem we have is that in an in-situ application, your timing or your time interval is more dependent upon hydraulic limitations, right? You can only get so much fluid into your system before you get daylighting and groundwater turning into surface water on your site. So I guess my answer is it depends on your application. In an Ex-Situ application, if you're destroying, say, PFAS and IDW in drums, you can apply your oxidants pretty quickly, maybe 15, 20 minutes apart. In an Ex-Situ setting, you're a lot more limited.
Okay, you kind of touched on this at the end of your presentation, Dan, but there's a question about can you or do you recover the catalyst after the application from the solution? I'm not sure if there's anything else you can add in response to that.
Yeah, currently, no, we don't recover the catalyst in In-Situ or Ex-Situ. Ex-Situ, I think catalyst recovery actually will be relatively simple. It'll be a physical process where, essentially you get your drum of contaminated water, you apply your catalyst and oxidant to the point where you achieve your remedial goals, maybe to the point where you can do a final carbon polishing step and discharge it to a sanitary sewer. And then you end up with a drum with a little bit of sediment on the bottom. All you have to do is recover that sediment physically and purify it so that you recover the catalyst out of that sediment. In an in-situ application, it's a lot more complicated because your silver catalyst is now in your soil, so it's much more difficult to recover.
Let's see, the next question is from David Raymond. Do you have any order of magnitude cost estimates for his application?
Yeah, great question. For Ex-Situ, if you're talking about really small volumes, honestly, this isn't a good technology for you because the mobilization costs are just going to outweigh your material costs. But in cases where, for example, if Parsons is out doing a field investigation and we're generating the IDW, we already have staff on site. I mean, we're looking at 30 to 50 cents a pound, perhaps. And that's primarily the catalyst and the oxidants, the catalyst of which you can recover. So it's really inexpensive, certainly much cheaper than incineration, and arguably less expensive in most cases in an Ex-Situ setting than granular activated carbon. Although in a setting where you're treating to the point where you can discharge the water, either to sanitary sewer, it makes more cost sense to use hot ISCO to destroy the bulk of the mass, PFAS mass in your IDW, and then to do a final polish with a GAT can.
Okay, the next question is, have you had success with any other oxidants?
That's a great question. So early on, we were optimizing our oxidant selection. So we tried hydrogen peroxide and the persulfate family, sodium, potassium, etc. And we got success in that all of the oxidants worked to some degree, but we found that the persulfate family works best. And at this point, through all of the work that we've done to balance catalyst loading and temperature dependent upon soil mineralogy and geochemistry, we're so far down the road with persulfates that we would likely stick with persulfates.
Let's see, next question is this reaction self-heating, or do you have to apply energy to heat the substrate? If so, do you have any ideas how this could be applied in the field?
Yeah, great question. It is not self-heating, so you do have to increase your temperature through another process. The beauty of this technology is you only need 10 or 15 degrees C. And, on a hot day, even in, upstate Michigan or northern Wisconsin, you can achieve those temperatures with just solar heating. So, we use black tanks and black hose, and we can easily achieve 40 C in the water prior to injecting it. Once the water is injected, of course, it's going to quench very, very quickly to your soil temperature. But the radicals that we produce only last a couple minutes anyway. So the radicals, by the time the temperature drops and you quench against your soil, your radicals are consumed and passivated anyway. So we don't have to apply something like steam injection or electrical resistive heating to get our temperature rise. Now that also means that this is not a technology that you would apply efficiently in January, in upstate Michigan, because you're not taking advantage of the natural heating you would get through solar heating.
Okay, next question is, can you explain how this technology would be applied in situ?
Yeah, sure can. So this technology would be applied like any other injection technology. First, we would install a series of injection wells or direct push injection points, and we would inject the catalyst first. So water with catalyst mixed in is injected, and we achieve our radius of influence, whatever the planned ROI is, and then we would follow up using the same injection wells or direct injection points with iterative oxidant applications such that you're injecting the oxidant in the same location you injected your catalyst, and you get that recycling effect within the soil matrix that you're impacting during injection. So it's a standard injection methodology.
Okay, next question is, do you have team members in Canada that are doing PFAS studies?
No, we don't. We, well, so I mean, our R&D lab is in Syracuse, New York, so we're not going to move the lab, but we would be more than happy to get samples from impacted sites in Canada, ship them to our lab in Syracuse, and give them a try. Same offers open for Canadian clients as well as U.S. clients. But currently, we don't have any research going on in Canada on Canadian sites.
So we got a couple more questions. Has the effect of co-contaminants, hydrocarbons, CVOCs, etc., been quantified for reductions in efficiency and/or percent destruction?
Great question. So the beauty of chemical oxidation or oxidative approaches is it's already been demonstrated, many times over the last 20 years or so for petroleum constituents, chlorinated solvents, some pesticides, organometals. So there's a body of knowledge that's out there to demonstrate the technology works. This is simply a modification, well, not a simple modification, a very complex modification, but a modification of standard chemical oxidation. And we're actually producing radicals that are more reactive than typical. And those radicals would destroy petroleum constituents or solvents, just like your standard, persulfate radicals. In terms of an inefficiency, we haven't demonstrated it in the lab in terms of, applying hot ISCO to a mixed contaminant, matrix. But it's easily calculated in that we can calculate the oxidant demand for, X% of petroleum constituents or Y% of solvents, so that we can pre-design the application to destroy the co-contaminants in addition to the PFAS. It would actually be an interesting laboratory study to get a sample from a site which has co-contaminants, do the calculations to account for the oxidant demand by those co-contaminants, and then run it at the lab and proof out our calculations. I don't see any reason why it wouldn't work, but it'd be a really interesting study.
Okay, we'll take one last question before we wrap up. Does anaerobic versus aerobic conditions get considered for hot ISCO?
Yeah, for sure. Aerobic is best because this is an aerobic approach. We could apply this in a naturally anaerobic environment. It would just be inefficient. Honestly, it would be a lot more expensive, because you would have to apply enough oxidant to convert your geochemical conditions first, and then apply your hot ISCO. So you're looking at more oxidant demand. And when you shift geochemistry on a site, especially from anaerobic or anoxic to oxic, you get a lot of other problems like precipitation of iron in particular. So that would have to be considered to ensure that we're not making a bigger mess than we're solving. But it is possible, and it's very much doable. It would just be inefficient.
Okay, I know that was the last question, but one more and then we'll wrap up. So if you have one catalyst application in situ and multiple iterative oxidant applications, do you anticipate hydraulic non-sinking in the field for catalyst and oxidant?
Hydraulic non-sinking. So I think you're asking, is there potential for the catalyst to sink vertically below your application interval? Possible, but the concentrations we're putting in are low enough that we're not getting, density derived vertical migration, either with the catalyst or the oxidant. And when the catalyst is being activated, when you apply your oxidant, the catalyst goes to a +2 state, which is non-soluble, and it'll actually drop out of solution until the oxidant is consumed, and then it'll drop to +1 and be soluble again. So I don't think you would get density derived vertical migration, but it's an interesting question. And considering that, like in a source area, PFAS likes to hang out right at the water table. You generally would apply hot ISCO, in the top, perhaps 10 feet of the saturated zone. You would have to look out for the potential for losing your catalyst, which means that you might have to put in more, increases your cost, but you certainly could put in more.
Okay, I think we'll wrap up Q&A there. If there's any other questions that anyone thinks of after the presentation, feel free to reach out to our presenter directly. His contact information is posted up here. A link to the page form has been posted. If you had any issues accessing that and want a professional development hour credit, please contact us and we'll follow up with you after the webinar. Next slide, please. So our next webinar will be on August 14th on PFAS and ecological samples and implications for risk assessment, presented by Jennifer Benning and Mark Rigby at the same time as today's webinar, 12:30 to 1:30 p.m. Eastern. So thank you to everybody who joined us for today's webinar, and we hope to see you again in August.
Thanks all for your time. Have a good day.